In Unit 6, we talked about local minimums and maximums, absolute minimums and maximums, and when a function was increasing and decreasing based on the derivative. We also discussed critical values that we found when we took the derivative, set it equal to 0, or when the derivative doesn't exist. We're going to continue that discussion in Unit 7 by talking about concavity, and then two other topics, L'Hopital's rule and graphing. Graphing is really putting everything together from both Unit 6 and 7 into one picture. So let me just read through this slide and then we're going to discuss what it means. The first derivative test. Let f be a function that is continuous on the interval I. Suppose that c is a critical number of f and ab is the open interval in I containing c. If f prime of x is greater than 0 for all a less than x less than c, and f prime of x is less than 0 for all x in between c and b, then f of c is a local maximum. If the opposite is true, if f prime of x is less than 0 for all x in between a and c, and it's greater than 0 for all x in between c and b, then f of c is a local minimum. If f prime of x has the same size on both sides of c, then f of c is neither a minimum nor a maximum. So as I said, that gets really complicated looking in all those words on the previous slide, but let's just put it into real English. If c is a critical number and f is increasing on the left and decreasing on the right, then we have a maximum. So if we're increasing and then decreasing, we have a max. And the opposite is true. If the critical number f it's decreasing on the left and then increasing on the right, we have a minimum. So again, while those looked really complicated, that's all it's telling us. If our derivative goes from positive to negative, at our critical number, we have a max, and if our derivative goes from negative to positive, we have a min. So example 1 on page 313 asks us to find the local extrema for f of x equals x to the fourth minus 4x cubed. So the first step is always to find our critical numbers. We take our derivative and set it equal to 0. We'll factor out a 4x squared. And we get x minus 3 and set each piece equal to 0. So one critical number is 0 and my other critical number is x equals 3. Now I like to make a number line and see what happens on either side of my critical numbers when x is 0 and when x is 3. So let's test the number, any number I want that's less than 0. I'm going to pick an easy one to plug in. Let's say -1, that's a nice easy number to plug in. We're going to test -1, and all I care about is if it's positive or negative. So f of -1, that's going to be 4 times -1 cubed minus 12 times -1 squared. So that's going to be a -4, and then minus 12, that's definitely going to be a negative number. Now let's test a number in between the interval of 0 and 3. Again, 1 is a nice easy number to test. It does not matter which number you choose in between the interval. It's generally just easier to choose numbers that are easy to test. So 4 times 1 cubed minus 12 times 1. Let's see, so that's 4 minus 12. That's also negative. And then let's pick a number bigger than 3, so maybe 4. So f prime of 4. 4 times 4 cubed minus 12 times 4. Well, that's going to be a positive. So let's summarize what this is showing us. As long as we are less than positive 3, so on the interval of negative infinity to positive 3, our derivative is negative, so our function is decreasing. And on the interval from 3 to positive infinity, our derivative is positive, so our function is increasing. So if we're going from negative to positive, we have a local min. And at x equals 0, we have neither a minimum nor a maximum because we continue to decrease. So at x equals 3, we have a local min. Example 2 on page 314 asks us to do the same thing. Find local extrema for f of x equals x to the 2/3, x minus 5. So this is going to be a product rule problem, and I'll set up my u and my v. So my u is x to the 2/3, and my v is x minus 5. My u prime is 2/3 x to the negative 1/3, and my v prime is 1. So my derivative is 2 over 3 times the cubed root of x times x minus 5, and then plus 1 times x to the 2/3, or 1 times the cubed root of x squared. I wrote them this way because I think it'll be a little bit easier for us to simplify, because our next step is to set this equation equal to 0. And in order to be able to set my fraction with my numerator equal to 0, my denominator equal to 0, to find my critical numbers, I need to make a common denominator so I have just one term. So let's see, this is over 1. So I need to multiply the second fraction by 3 times the cubed root of x in both the numerator and the denominator. So I have 2 times x minus 5 over 3 times the cubed root of x, and then plus. Now I have x to the 2/3 and x to the 1/3. Well, that makes x to the 3/3. So 3 times x over 3 times the cubed root of x. So now that I have a common denominator, I'm going to distribute that 2 and combine my like terms. So 2x minus 10 plus 3x all over 3 times the cubed root of x. So 5x minus 10 over 3 times the cubed root of x. And now I take a look and see, when does this derivative equal 0 and when does it not exist? Well, it equals 0 when my numerator is equal to 0, and it does not exist when my denominator equals 0. So let's set each of those equal to 0 and see what my critical numbers are. So 5x minus 10 is 0. So 5x is 10. So x is 2. And then the cubed root, 3 times the cubed root of x is 0. And that's going to happen when x is 0. So I have two critical numbers here at x equals 0 and x equals 2. So let's again make our little reference sheet here with our number line. And we're going to be plugging into anywhere I want, but I'm going to choose the easiest place to plug in, which looks like this derivative right here, 5x minus 10 times 3 times the cubed root of x. That looks like the most simple one to plug into. I could choose any other version of it. I could choose this first version, the second version, or the third version, or this final simplified version. Whatever makes sense to me is what I'm going to choose. So let's plug in a negative 1. 5 times negative 1 minus 10, that's going to be a negative on the numerator, and 3 times the cubed root of negative 1 is a negative on the denominator. So a negative over a negative is a positive. And now let's plug in positive 1. 5 times 1 minus 10, it's going to be a negative on the numerator. 3 times the cubed root of positive 1 is a positive on the denominator. So negative divided by positive is a negative. And then let's plug in something like 3. 5 times 3 minus 10, that's positive. And 3 times the cubed root of 3 is also positive. So positive over positive is positive. Again, I don't care about the numbers. I only care about the signs because I want to know if we're increasing or decreasing. So it looks like to me we increase until 1, then we decrease, and then at 2 we turn around and we increase again. So I'm going to have a maximum at x equals 0 and a minimum at x equals 2. You're going to see me use this shorthand a lot because it makes sense to me. If it doesn't make sense to you, there's a lot of other ways that you can write things out, such as using a table as they do in the book. As I said, that's on page 314, or writing it out more longhand. But this shortcut makes things a little more summarized for me. So let's just finish off what we're going to say. We have a max at x equals 0 and a min at x equals 2. In example 3 on page 314, they give us a picture. It's figure 36, and this is the derivative. That's really important. I want to stress that again. They're giving us the function, the derivative, the picture of the derivative, and they're asking us to find some stuff. So when it's asking in part A, it wants to know, determine the critical numbers of f. So the critical numbers occur when the derivative equals 0 or the derivative does not exist. So I'm looking at, when does this picture equal 0? Well, it looks like it happens here and then again at here. So at x equals 0 and x equals 2. Those are my critical numbers because that is when the derivative equals 0. I don't have any in this picture when the derivative does not exist. That's a really important distinction to be making. I'm looking at this picture when the derivative equals 0. So when is my y value in this picture equaling 0? Now it wants to know, when is the function increasing? Well, the function's increasing, f is increasing when my derivative is positive. So I'm looking at my picture and it looks like my derivative is positive from 2 all the way up through infinity. So we're positive here. This is positive. And now I'm looking for, when is my function decreasing? Well, my function decreases when my derivative is negative. And we're negative all the way from, it looks like negative infinity, and we stay negative, and then we keep negative. So we have a little blip at 0, so we go from negative infinity to 0, and then from 0 to 2. We are not negative at 0 because at 0 we equal 0. So that's why 0 is not included in this interval. And then let's see, at what point does x, if any, have a local min or a local max? So let's see what's happening here. I'm going to make a little number line, and hopefully that will help. I'm actually going to make it up here for part D. So here's 0, and here's 2. Less than 0, we're still negative. Between 0 and 2, we're negative. And greater than 2, we're positive. So it looks like my function decreases, and then turns around and increases. So at x equals 2, I have a minimum. And at x equals 0, although it was a critical value, it is neither a minimum nor a maximum. So let's take a look at the first derivative test for rectilinear motion. So that's motion where we're going left and right. And we're talking about velocity. The summary of this is, when the velocity is positive, so the first derivative position, the distance from the origin is increasing with time, so we're moving to the right. And when the velocity is negative, we're decreasing, so we're moving to the left. When the velocity is 0, the object is at rest. So the same exact idea as the first derivative test, we're just putting it towards velocity. So let's take a look at example 4 on page 315. An object moves along a horizontal line so that the distance s from the origin at any time t greater than 0 in seconds is given by s equals t cubed minus 9t squared plus 15t plus 3. Determine the time interval during which the object's signed difference from the origin is increasing. That is, when is the object moving to the right? And then B is asking us, when is the object moving to the left? C wants to know, when does it reverse directions? And then D wants us to draw a picture of this. So let's start by first finding the derivative. So we're looking for the velocity. And we get 3t squared minus 18t plus 15. And we're looking for, when do we have our critical numbers or our turning points, and we'll set it equal to 0. We'll factor out a 3, and then let's factor that to 5 and 1. So it looks like it happens, the velocity is 0 at time 5 and at time 1. So let's take a look at this picture. I'm going to draw my sign chart again. Again, if the sign chart doesn't help you, then you don't have to do it, but it helps me, so I'm going to do it. It says I can be greater than or equal to 0, so I'm going to plug 0 into my derivative because I think it would be easiest, and the derivative that I'm going to use is this first one up here. If it's not helpful to you, you can use a different one. You're welcome to use the second or the third one that we've set up there. What I mean by that is this one or this one. So whichever one makes it easier for you. If I plug in 1/2, I'm going to get a negative times a negative or a positive. And if I plug in 2, I'm going to have a negative times a positive or a negative. And if I plug in 10, I have a positive times a positive or a positive. So that means I'm changing directions twice, and the 2 times that I'm changing directions are here at 1 and here at 5. And my derivative is positive when x is less than 1 and when the time is greater than 5. So we're moving to the right between 0 and 1 and between 5 and infinity. And we're moving to the left between 1 and 5. And we change directions at t equals 1 and t equals 5. Now, drawing a picture of this, you probably haven't seen this before. So let's take this kind of slowly. We're going to want to know where these points are. What's the position at time 1 and at time 5? So before I draw my picture, I'm going to make a little XY table to help me figure that out. So I have my time and my position. So at time 1 and at time 5. So I'm going to plug 1 into my position function, and I get 10. And I'll plug 5 into my position function, and I get a negative 22. So the way we graph this is we have our time axis here. So here's our position, and let's see, there's 0, 10, 20. So we start at 0 and we move to the right until we've gone for 1 second, which puts us at a position of 10. And then we go to the left until we've gone 5 seconds, and then we go to the right. So this is at the point t equals 1, and this is at the point t equals 5. I know that looks really different than any function drawing you've ever done before, but that's how we draw position functions. The next part of the problem, part E, asks us to find when is the object's velocity increasing and when is it decreasing. So when is the velocity increasing and when is the velocity decreasing? So this happens. The velocity increases when our acceleration is positive, and the velocity decreases when our acceleration is negative. This is exactly the same concept as when was our position moving to the left or right based on our first derivative, but this time now we have our second derivative. So let's take a look at acceleration, which is 6t minus 18. We'll set that equal to 0. So that happens at t equals 3. I'm going to make the exact same little picture here to help me figure out what's going on. And let's plug 1 in. When I plug 1 in, I get a negative. And when I plug in, let's say 4, I'm going to get a positive. So our velocity is decreasing when our acceleration is negative, or between the time 0 and 3, and our velocity is increasing between the time 3 and infinity, or when t is greater than 3. Again, that's because my acceleration is positive. So everything we've done until this point has been pretty much a review of the previous 4.1, 4.2, 4.3. But now that we're at to concavity, this is something completely new. And it's a little bit different to think about, but you might have heard about concave things in science class. You might be concave or convex. In math, we're going to call it concave up or concave down. So I like to think about concave up as you can hold water. So here, if I poured water in, I could hold it. Those are concave up. And here, if I poured water in, it couldn't hold it. Those are concave down. So they're like upside down and right side up, if you want to think about it that way. So when our second derivative is positive, we're concave up. And when our second derivative is negative, we're concave down. And we can be concave up and increasing or concave up and decreasing. Here, this is a function that is decreasing but concave up. And this is a function that is increasing but concave up. Here we have a decreasing concave down and an increasing concave up. So let's just be a little bit more specific. My derivative here, my second derivative is positive, but my first derivative is negative. That's how I got decreasing concave up. My second derivative is positive, and my first derivative is positive, so I'm increasing and concave up. My second derivative is negative, but my first derivative is also negative, decreasing and concave down. And my second derivative is negative, as well as my first derivative is positive, increasing and concave down. I know these look a little bit weird, and they're definitely different than things that we've done before, but they'll start to make sense very soon. Example 5 on page 318 asks us to show that f of x equals e to the x is concave up on the domain. So first I find the first derivative, which is e to the x. Then I find the next derivative, the second derivative, which is also e to the x. And since the second derivative, e to the x, is always positive, then I'm concave up all the time. How I find where I'm concave up and concave down is exactly the same as how I find when I'm increasing and decreasing. The same idea. So the first thing I do is find my first derivative. So 3x squared minus 12x plus 9. And since I want to know my local extrema, my local mins or maxes, I set it equal to 0. See, we'll factor out a 3. And that's going to happen at 3 and at 1. And then I'm going to make my sign chart. And let's see, if I plug in a number less than 1, I'm going to pick 0 because it's easiest. I get a positive. And if I plug in like the number 2, I'm going to get a negative. If I plug in the number 5, I get a positive. So let's say I go up and then down and then up. So it looks like I have a max at x equals 1 and a min at x equals 3. All right, so now to find where I'm concave up and concave down, before I continue, I want to talk about these points. These are called the critical values, these numbers right here. When I set them equal to 0 and solve, those are my critical values. When I do the second derivative and solve, I'm finding points of inflection. So they have a different name, but the same process for finding them. So I take my second derivative, see 6x minus 12, and I set that equal to 0. And that happens at x equals 2. And again, this is a point of inflection. And we're going to do the same thing. So let's plug in 0 and I get a negative, and if I plug in 3, I'm going to get a positive. So I'm concave down when x is less than 2, and I'm concave up when x is greater than 2. So let's talk a little bit more about points of inflection. So I'm just going to read you the definition and then we'll talk a little bit about it. Suppose that f is a function that is differentiable on an open interval a to b containing the point c. If the concavity of f changes at the point c, then c is a point of inflection. The distinction that they're making here is just like the distinction that we make when we have critical numbers. Sometimes we don't have a critical number, even though the derivative equaled 0 or the derivative did not exist at that number. So sometimes it's a possible critical number, but it turns out that the direction doesn't change. Same here. Even though we think it might, the concavity might not change. So how we find that? We take the derivative, the second derivative, and we set it equal to 0, or it does not exist. Then we find the test for concavity using the positives and negatives. And then if the concavity changes, then we have a point of inflection. If it doesn't change, if it doesn't go from concave up to concave down, we do not have a point of inflection. All right, let's find our points of inflection on example 7 on page 319, f of x equals 5/3 x. So we first find our first derivative. So 5/3 x to the 2/3, and then we find our second derivative. 10/9 x to the negative 1/3. And I'm going to rewrite that as 10 over 9 times the cubed root of x. And we're concerned when our derivative does not exist or when our derivative equals 0. So since our derivative can't equal 0, I'm going to ignore that part. But here my denominator can be 0, so there is maybe a point where my denominator does not exist. So let's set it equal to 0, and that's going to happen at x equals 0. So at x equals 0, my denominator doesn't exist, so my second derivative doesn't exist. And let's make our little sign chart here. And let's see, if we're going to plug in a number that's negative, that's going to be 10 over a negative number. That's negative. And if I plug a number then that's positive, that's 10 over a positive number. So I'm concave down. I know it didn't ask us for this, but I'm going to write it out. I'm concave down when x is less than 0, and concave up when x is greater than 0. So x equals 0 is a point of inflection. So in example 8 on page 320, we're given two pictures. The first one is the derivative, and the second one is the second derivative. So these are not the graphs of the actual function f. These are the graphs of the derivative of f and the second derivative of f. So if I'm looking for my critical numbers, again, that's when my derivative equals 0. So that happens here and here, or when my derivative does not exist. And I don't seem to have a point where my derivative does not exist. So that looks like it happens at x equals 0 and x equals 4/3. When is the function increasing? Well, that happens when my derivative is positive, so that's between negative infinity and 0, and 4/3 and positive infinity. When is my derivative decreasing? Well, that's when my derivative is negative. That happens between 0 and 4/3. So I'm looking at that area. And when at which numbers do I have a local minimum? So, and then a local maximum. I have some trouble looking at this picture to tell me which one's a minimum and which one's a maximum. So I like to put them on a number line, with my critical numbers being 0 and 4/3. And then I make my sign chart. Again, if this isn't helpful to you, you don't have to do it. Less than 0, I'm positive. Between 0 and 4/3, I'm negative. And greater than 4/3, I'm positive. So I go up and down and up. So I have a max at x equals 0. And here I have a min at x equals 4/3. For the next part, it asks me when is it concave down and when is it concave up. So this time I'm going to look at the second derivative, because concave up is when my second derivative is positive and concave down is when my second derivative is negative. So let's see, my second derivative is positive when it's greater than 1, so between 1 and infinity, and I'm concave down. I'm concave down from here to here, and then I'm 0, and then from here to here. So concave down from negative infinity to 0, and then from 0 to 1. Now let's make, again, I like to make my sign chart to help me figure out about my points of inflection or my turning points. So 0 and 1 are my possible critical values, in points of inflection, because that's where my second derivative equals 0. So less than 0, I'm negative. Between 0 and 1, I'm negative. And greater than 1, I'm positive. So the only turning point I have is this one right here at x equals 1, because that's when my second derivative actually changes signs. 0 doesn't count because I go from negative to negative, so it's not a point of inflection. Now the second derivative test, I'm going to be honest, is not my favorite test. It's not something that I use a lot, but it is useful occasionally, and you might prefer to use it, so I want to make sure that I give you the option. The second derivative test, it tells me that if I have a critical number at c, then if my second derivative is negative, then I have a local max. And if my second derivative is positive, I have a local min. So that's exactly the opposite of what you expect to see that happens. At your critical number, I'm going to say it again, at your critical number, if you have a negative second derivative, you get a max. And if you have a positive second derivative, you have a min. So on example 9 on page 322, they want us to first find where I'm concave up and concave down, then find my points of inflection, and then finally use the second derivative test to find any extreme values. So I'm going to start by finding my first derivative. Let's see, 1 minus 2 plus 2 sine x. We'll set that equal to 0. And sine x is going to equal a negative 1/2, and that happens when x is 7 pi over 6 and 11 pi over 6. Now you might need to look back at your unit circle to see when that happens, and remember your sine is your y value. Okay, so we're going to keep going. We're looking for concave up and concave down, so let's find the second derivative. I'm going to need these numbers in a little bit, but I'm just going to leave them alone for a second. So 2 cosine x, and again we'll set that equal to 0. So that's when cosine x equals 0. That happens at, so if you're not positive about cosine, let's draw the picture. We go 1, 0, negative 1, 0, positive 1. So that's going to happen here at pi over 2 and here at 3 pi over 2. Of course, you could have used your unit circle, but sine and cosine, you really should be able to graph or at least memorize between 0 and pi, and then it should repeat for you. All right, so let's see if where we're concave up and concave down. We're going to make our little number chart between pi over 2 and 3 pi over 2. So let's plug in a number between 0 and pi over 2. So we could choose pi over 3. And the cosine of pi over 3 is 1/2. So 2 times 1/2 is a positive. And then let's pick a number between pi over 2 and 3 pi over 2. Let's pick pi. And cosine of pi is here negative. So 2 times negative 1 is still negative. And 3 pi over 2, let's pick a number that's larger than 3 pi over 2. So we can pick 5 pi over 3. So that's the cosine of 5 pi over 3 is 1/2, and 2 times 1/2 is a positive. So we are concave up between 0 and pi over 2, and between 3 pi over 2 and 2 pi, because that's the domain that they gave us here. And we're concave down between pi over 2 and 3 pi over 2. Now our points of inflection are at pi over 2 and 3 pi over 2 because we changed concavity there. And it wants to use the second derivative test to find our local extrema. So to do that, we're going to do the second derivative of 7 pi over 6 and the second derivative of 11 pi over 6. So that's the reason that I found those in the beginning and then I just left them alone, because I need to test my critical numbers. So let's see, 2 times the cosine of 7 pi over 6. So the cosine of 7 pi over 6 is negative root 3 over 2, and 2 times negative root 3 over 2 is going to be a negative. So that means we have a maximum at x equals 7 pi over 6. And 2 times the cosine of 11 pi over 6 is positive root 3 over 2. So 2 times positive root 3 over 2 is going to be positive. So we have a min at x equals 11 pi over 6. As I said before, I prefer to do my sign chart to find my mins and maxes, but this second derivative test is definitely an alternative to that. So just a summary of the second derivative test. If at the second derivative the function does not exist at the critical number, the second derivative cannot be used. And if it equals 0, then the second derivative test can also not be used. So we only get information if the second derivative is positive or negative, not if it does not exist or is 0.